Hey everybody, it's Mr. Covey here, and today we'll be talking about parametric second derivatives. Okay, so this is kind of one of those things that has a little bit of a trick to it, and students mess it up a lot because they don't remember this kind of weird thing about it. Okay, so basically I'm going to spend a lot of this video just kind of deriving this formula, or showing you why this formula is the weird way it is, but then at the end of the day you just need to remember that it works this weird way. Okay, so to start, sorry, give me a second. Have you ever wondered why there's kind of this weird situation with the squareds going on with the second derivative? So you write d squared y dx squared, and you're like, I get the squared part because it's the second derivative, but why is the squared in different parts? So there is a reason behind that, obviously, and the reason is to find the second derivative, you take the first derivative, dy dx, and you take the derivative of it with respect to x. Okay, the first derivative usually has x's in it, and you take the derivative with respect to x. So if you look at this and you do some algebra, which this really isn't like officially legal algebra, but the idea is there. This is d squared y. The bottom is dx dx. It's dx squared. There's two dx's. Keep the top the same. Get lazy on the bottom, which isn't good, and write it as dx squared, and you end up getting this kind of seemingly weird notation. It actually kind of makes sense. Okay. If you're super confused about this whole derivative with respect to thing, like, it is an important idea. Like, remember, why do we call it dy dx in the first place? Well, because you're taking a function y and you're doing the derivative with respect to x. And if you do the derivative with respect to x of a function called y, we call it dy dx. Okay. I forgot to mention, if you go by the numbering in your packet, I think this is page 17. Cool. Okay, so let's actually look at a function. So we're looking at this parametric function. We can graph it just by tossing it in our graphing calculator. Lemke showed you how to do that. And if we let t be any real number, we end up getting something that looks like this. And if you graph it with that ball and chain like Lemke talked about, this graph moves kind of in this direction. And so as the t-values increase, with this being what happens when t equals 0, we're at the 0.00. So you put little arrows going that way to let the person know the graph goes there. Okay. Okay. So we're going to use this graph kind of as our example when we think about the second derivative of a parametric. Okay. So first off, just looking at this graph, I want you to think for a second. We got something that goes shoo, shoo. I want you to think about what you know about dy dx, dx dt, and dy dt. Okay, Lemke talked about the difference between these. We practiced with it. Look at this graph and just think for a second what you know about dy dx, dx dt, and dy dt. Okay. Okay. So remember, dy dx is the slope of the tangent line. So if you think about your slope of your tangent line is positive. Literally, we're talking about the slope. The slope is positive, 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 undefined, positive, 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 positive. Okay. What about dx dt? Well, dx dt, you remember, is right and left. So we're moving left, 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 right, 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 right. So dx dt would be negative, positive. Remember, dy dt is up and down. So we're moving up, 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 up. So it'd be positive. Cool. Just want to make sure we're keeping track of the difference between dy dx, slope of the tangent, dx dt, horizontal movement, dy dt, vertical movement. Okay. All right. Let's get into this second derivative stuff. Oh, no, wait. Let's do the first derivative first. Fine. So as a reminder, because you do need it, how do you take the first derivative of parametric? This formula that Lemke talked about, dy dt over dx dt. Makes sense. How do you get dy dx? You do dy dt divided by dx dt, gives you dy dx. Okay, let's do that real quick. We'll do dx dt first, it's on top. Dx dt, the derivative of that x thing with respect to t would be 2t. Dy dt would be 3t squared. Stack them. dy dt over dx dt. We can simplify that. And there's dy dx. Okay. That's our first derivative. Now I know what you're thinking. Oh, okay. So the second derivative? Well, I'm sure you just take the first derivative and then do one more derivative. No. No. It's a little more complicated. Okay? And, excuse me, before I show you how it's more complicated, remember that d squared y dx squared tells you concavity. So if you look at our original function, we should get negative concavity followed by positive concavity. Negative, and then it's positive. It's concave down and then concave up. If the rule was just take dy dx and do another derivative with respect to t, we just get 3/2, which would imply this thing is always concave up, which it's not. It just said it was concave down for part of it and concave up for the other part. So this rule has to be a little more complicated. I'll show you how it's more complicated. Stick with me, I'm going to do a little derivation here. It's going to be a little confusing. Just try and stick with me. This is what Lemke talked about the other day. The derivative with respect to x of a function y is called dy dx. When we're talking about parametrics, we find that by doing the derivative of the y thing with respect to t and the derivative of the x thing with respect to t. Okay? If you think about the way this looks, okay, the basic idea is you do the derivative of the thing in parentheses, toss it in the numerator, and put it over dt. And then you grab the denominator and put it over dt. Okay, that's kind of the general structure. I'm trying to show you that with the yellow and blue and pink. And those two dt's are both there. They end up canceling, that's why it's dy dx. If we think about that same idea with a second derivative, we're not doing d dx of y, we're doing d dx of dy dx. So what goes on top? Well, dy dx, the derivative of dy dx. We toss it over a dt, and we put a dx dt on the bottom. This is the formula for how you find the second derivative of a parametric. The very, very weird part is this extra dx dt on the bottom. Okay? Here's the same thing written out a different way. The first derivative of a parametric is dy dt over dx dt. That gives you dy dx. To find the second derivative, you don't just do another derivative of that with respect to x. Okay? Instead, you do another derivative of that with respect to t, but then you divide it by dx dt. Okay? This is the weird part of this formula. You do need to know this formula. Basically, the idea is, hey, you do the second derivative, but then you divide it by dx dt one more time. That's the idea. That's what you need to remember. And this blue thing is the weird thing that people forget about. Okay, I will show you. It's just going to help to see an example. Okay, so let's go back to our original thing here. Yeah, we already did this. So we got that dy dx was going to be 3t over 2. And now we want to find the second derivative. Okay, well, again, people think, oh, you just do one more derivative, and you get 3/2, and I'm like, yeah, sure, except for you have to take that and divide it by dx dt. So you take the second derivative with respect to t. You did a derivative again, but you got to divide it by dx dt. Okay, so you got to toss down here whatever dx dt was. And remember, we said dx dt was just 2x. Or 2t, rather, excuse me, was 2t. So we have to toss an extra 2t down there. That's the weird part, okay? So if you simplify this, you get 3 over 4t. And this is our second derivative. And if we go back to our graph, well, when is our graph concave up? Well, we said our graph was concave up for this chunk, and this chunk is when t is bigger than 0. That's when my graph is bowl-shaped. And if you look at our second derivative now, this all makes sense. Okay, my second derivative is 3 over 4t. When is 3 over 4t greater than 0? When t is greater than 0. Okay, that's when the graph is concave. Cool. Okay, I just want to jump through 2 example problems with you guys. Go to page 19 if you're going by the numbers in the bottom right. I want to do an example here. It says, hey, I got a parametric. Cool. On what intervals is the function moving to the right, to the up? When is it increasing and when is it concave up? Okay. The first thing to do is make sure you understand these different terms and what they mean in terms of the derivative. This is big kid math now. You can't just say the derivative. You're like, well, what derivative? Okay. So moving to the right means my x values are increasing. In other words, dx dt is positive. Moving up means my y values are increasing. My y values are increasing, meaning dy dt is positive. If I literally want to know when my function is increasing, that is when the tangent line has a positive slope. That is when dy dx is positive. And if I want to know when my function is concave up, that's when the second derivative is positive. Take a look at this. Know this. This is important. I can't tell you how many kids I ask, when is the function moving up? And they tell me when dy dx is positive. I'm like, nah, bro. Nah. All right, so then let's actually do this. Why don't you pause and try and calculate these 3 things to start. Okay, we'll probably do this. Let's finish it up together. So for dy dt, I got 2t for dx dt, I got 2t. For dy dt, I got 2t plus 6. For dy dx, I stack those, simplify it. I got 1 plus 3 over t. Now to do the second derivative, I do need to do the derivative of this. And it might be helpful to rewrite this as 1 plus 3t to the negative 1, so that when I do the derivative, I get negative 3 over t squared. But then don't forget, that's not my second derivative. I then need to, I'm just going to write down here. I then need to stack that over dx dt. Don't forget about that. That's the weird part of the formula. Going back, that's the weird part of the formula. It's got that extra dx dt on the bottom. So I found the second derivative, and then I throw an extra dx dt on the bottom. Okay? I'm going to simplify this, and so for the second derivative, I get this. And now I can go back and answer these questions real quick if I want. So when is it moving right? When is dx dt positive? When t is greater than 0. When is it moving up? Well, when is that positive? When t is greater than negative 3. When is it increasing? When is this thing positive? Well, when t is greater than negative 3. And then when is it concave up? When is this thing going to be positive? Here's my little inequality. I'm trying to figure out when this is greater than 0. Well, when is negative 3 divided by 2t cubed going to be greater than 0? Well, if in order for this to be positive, the numerator is negative, so the denominator needs to be negative. So when is t cubed less than 0? When t is less than 0. And it'd be nice maybe, too, to write these in interval notation. So when t is less than 0, in other words, where t is between negative 0, or negative infinity and 0. Or we could write t is less than 0. But I made a mistake on increasing. Let's do this out together, shall we, friends? Okay, so this is dy dx. I want to figure out when dy dx is less than 0. Or sorry, greater than 0. Because I want to know when it's increasing. When dy dx is greater than 0. To solve this inequality, it might just be helpful to figure out when it equals 0. Okay, so t equals negative 3 would make it equal 0. What's another t value that would mess with this? Well, t equals 0 would make it undefined. And then we should just do a little sign chart to solve this inequality. So at t equals negative 3, it's undefined. Or excuse me, it would be equal to 0. At t equals 0, this first derivative would be undefined. And so then I just need to do a little sign chart and see like, okay, well, if I plug in negative 5, it's going to be true. It's going to be greater than 0. If I plug in negative 5 here. If I plug in negative 1, dy dx is going to be negative. And if I plug in 5, dy dx is going to be positive. So where is it actually increasing? Where is dy dx positive? Negative infinity to negative 3, 0 to infinity. I'll just be careful with that. I guess I was messing that up. Sorry. Cool. And again, we can write these in interval notation if you want. T is greater than negative 3 to infinity. T is greater than 0, 0 to infinity. Okay. I want to do one more problem with you guys. And that is page 23. Check. Let's just do this first one together. Okay. So it's saying x equals t squared, y equals t squared plus 6t plus 5. Figure out dy dx, the second derivative, d squared y dx squared, and on what intervals the curve is increasing concave up. Okay? Wait, that's the exact same problem. My bad. Let's do number 2. Do number 2. Change my mind. Pause, give number 2 a try. Okay. So for number 2 here, dy dt, dx dt. How do I find dy dx? I stack those over each other. Again, the reason I'm finding dy dx, they didn't tell me here, is because I'm trying to figure out where it's increasing. Increasing means dy dx is positive. Okay? So I take dy dt over dx dt, simplify. Here's dy dx. Okay? So on what intervals is the curve increasing? Well, it's increasing when dy dx is positive, so when t is greater than 1/3. Second question says, when is the function concave up? That has to do with the second derivative. Again, here's the key thing to remember. Pay attention. Take my first derivative, do another derivative with respect to t. What's the derivative of 3t minus 1? 3. But that's not my second derivative. I also have to stack it over dx dt. This extra dx dt down here is the tricky thing. So my second derivative is actually 3 over 2t. When is that going to be positive? When is my function going to therefore be concave up? Is when t is greater than 0. Okay. All right. We'll practice with this. Thanks for watching, guys. That concludes this video.